Welcome back. Now we're going to look at the section 2.6, which talks about the numerical methods. And this is sort of a wrap-up section for the entire chapter. First, I'm going to talk about some of the theory behind numerical methods and the two main methods we'll be looking at, and then we'll look at the spreadsheet and demo the Euler worksheet that you will be using for your homework or part of your homework. Okay, so first, numerical methods are derived from the Taylor series expansion or similar representations of functions that you saw a little bit of in Calc 2. So let me remind you a little bit about what that means. Now here I'm going to use the function x of t to represent the thing, the t-dependent variable. And then t will be, the function of t will be moving away from a certain point, t sub j. So I have a fixed point that I know the function at. I'm going to be moving away from that point and evaluating the function where I don't know it. Okay? So the function x, a little bit away from the point we do know, is equal to the function at the point we know, plus a little bit, delta t, times the derivative, or the slope function we do actually know, at the original point, tj, plus more information like delta t squared over 2 factorial. 2 factorial, by the way, is just 2. That's okay. Times the second derivative at the point we know, the first function and the first derivative. And then higher and higher terms. You have delta t cubed over 3 factorial times the third derivative on up to the delta t to the nth power divided by n factorial times the nth derivative of x. And as n, we keep going as n goes to infinity. So that's the full series, the full power series for this shift. Now, since we know the function at our point tj, and we know the differential equation, x prime equals some function of t and x, we actually know everything up to here. And so the first method we'll be looking at, called Euler's method, or the Euler method, just uses this known information and estimates from there, which means we'll be ignoring certain amounts of information past that point. So for the Euler method, or sometimes called the forward Euler method, we let x sub j plus 1, which is just another way of saying, or way of approximating the function at t of j plus delta t. So x of j plus 1 is the next step, is equal to x of j, approximation of the function at t sub j, plus delta t times the slope at t sub j, x sub j. So this equality ignores a bunch of higher order terms, but the x's we're working with are approximations. They're not functions of t. They're discrete valued functions that we're getting to approximate that function of tx. Now this particular approximation, since it goes up to the first power of delta t, our error will actually grow proportional to that. We call it a first order method because the error grows proportional to the first power of delta t. Now the next method shown in 2.6 is called the Improved Euler method, and it has some other names too, but this is the main name we'll use to describe it now. And it gets a little bit more complicated. Well, let me give you a diagram to show you a little bit how it works. We work from the blue arrows that represent the slope field. And this black arrow is the example of the Euler method. We start with a point we know, x sub j, and we use the slope, f of t sub j, x sub j, and we follow it a certain amount of time, delta t. And that is our next point, x of j plus 1 for the Euler method. Now, for the improvements, what we do, instead of just following the original slope, we use the original slope, and then we also compare it to what we think the final slope is. So we think of this as m sub 0, initial slope. M sub 1 would be what the slope field tells us, the direction field tells us at that approximate value. And then we take those two slopes and average them. We know we assume there's some balance between them. Maybe One estimate underestimates, one overestimates. We find the average, the balance between the two. And that's the improved Euler method, where we take the average of the original estimate from Euler's method plus the function, the slope function at the next time point with the next x value approximation. So this information just describes how M1 slope is calculated. And then once we average those two, we get this green slope, and that's what we use, just as Euler's method, to move forward. We go from x sub j to the better x sub j plus 1 and try to follow this curve from the direction field a little bit better. Now, the book also has a method called Runge-Kutta, or the fourth order Runge-Kutta method. And this is a little bit more complicated than we'll dive into right now. You're welcome to take a class in Numerical Methods where we dive into the Runge-Kutta methods a lot more. But we'll just stick with these two methods in this class, differential equations. And now, let's look at the spreadsheet.